Bienvenido a la última de las actividades académicas que hemos tenido el gusto de celebrar alrededor del trabajo del doctor Nicholson, a quien voy a presentar a continuación una semblanza que hemos preparado, que es la misma que utilizamos el día de ayer para algunos de ustedes que, según veo, solo quiero mencionar que la razón por la cual estamos circulando una lista de correos y la razón por la que también lo hicimos durante el taller de la semana pasada es poder enviarles a aquellos de ustedes que nos demos cuenta que vinieron a la mayor parte de las actividades algunos anuncios que tendrán que ver con actividades relacionadas con los temas que trató Dan. Entonces voy a leer la semblanza. Actualmente Daniel J. Nicholson es investigador senior del Instituto Konrad Lorenz para la investigación en evolución y cognición, ubicado en Klosterneuburg, Austria. Obtuvo un doctorado en filosofía por la Universidad de Exeter, una maestría en historia y filosofía de la ciencia por la Universidad de Leeds y una maestría en biología molecular y celular por la Universidad de Vega. Ha sido investigador postdoctoral del Centro para el Estudio de las Ciencias de la Vida, perteneciente a la Universidad de Exeter y del Instituto Kohn para la Historia y Filosofía de la Ciencia y las Ideas de la Universidad de Tel Aviv en Israel. En Leeds estudió con los historiadores Jonathan Hodge y Gregory Radic. En Tel Aviv trabajó con la filósofa y feminista Eva Jablonka, y en sus dos periodos en Exeter ha colaborado con grandes nombres de la filosofía de la biología, especialmente Leigh Moss, John Brett, Paul Griffiths, Staffan Miller-Bean, Maureen O'Malley y Sabina Leone. Su trabajo se caracteriza por un enfoque integrativo y fuertemente interdisciplinario dentro del marco de la historia y la filosofía de la biología. Su investigación en los últimos años se ha centrado en la ontología de los sistemas vivientes, particularmente en las formas en que los organismos difieren de otros sistemas organizados complejos, como las máquinas, que fue el tema del taller de la semana pasada, y en las implicaciones que tienen estas diferencias para las teorizaciones y explicaciones de los mismos. También está interesado en muchos de los debates tradicionales en la filosofía de la ciencia, así como en la naturaleza de la relación entre la biología y la física. El tema de hoy, pues, tiene que ver sobre todo con esto. Sus artículos, que según Google Scholar acumulan conjuntamente más de 500 citas, han sido publicados en revistas tanto históricas y filosóficas como científicas. Entre sus proyectos colaborativos cabe destacar una edición especial en la revista Studies in History and Philosophy of the Biological and Biomedical Sciences, coeditado junto con Leigh Moss, que bueno, Leigh Moss está aquí en México, claro, como
ahora mismo no, pero sí.
Sobre normatividad y teleología en las explicaciones biológicas, y un libro publicado el año pasado por Oxford University Press, coeditado junto a John Dupré, quien estuvo de visita hace unos pocos días aquí en la UNAM, en la Facultad de Ciencias TV, que propone una visión procesual del mundo vivo, combinando metafísica y biología. Este último libro es de acceso libre, así que puede ser descargado gratuitamente para quienes estén interesados. Ha publicado sobre un gran número de temas, incluyendo la historia y epistemología de la teoría celular, el concepto de mecanismo en biología y el surgimiento de la filosofía de la biología como profesión a mediados del siglo XX. Su trabajo más reciente, publicado el mes pasado en Journal of Theoretical Biology, un análisis un tanto polémico de una serie de debates conceptuales en la biología molecular y celular actual, ha tenido una gran acogida por parte de la comunidad científica. Actualmente está escribiendo un libro sobre la perspectiva organicista en la biología, que ya el contrato con MIT Press, y otro junto con el filósofo de la biología e historiador alemán Jan Berke, que está en Bochum, sobre el origen y la posterior transformación de la biología teórica durante el siglo pasado. Entonces, pues sin más, Dani.
Muy bien, muchas gracias, Paco. Antes de nada, no sé si está conectado el micrófono o si tengo que hacer algo para... ¿Está bien? Bien. Muy bien, pues gracias, Paco. Estoy muy agradecido a todos por venir, un poco triste por pensar que es la última charla que voy a dar aquí en la UNAM. Ha sido una visita tremendamente estimulante. Voy a dar la charla en inglés, pero luego el turno de preguntas lo podemos hacer en español. Si tenéis alguna duda o algo que no entendéis, me podéis interrumpir en cualquier momento y lo resolvemos. Lo que voy a presentar hoy es un tema que estoy trabajando ahora mismo, no está publicado todavía, y en realidad pues estoy aprovechando, ¿no? el hecho de que en 2019 se cumple 75 años de la publicación de What is Life, de Erwin Schrödinger. Y nada, voy a tratar de ofreceros una perspectiva nueva de lo que creo que es el legado de este libro, de las ideas de Schrödinger en la biología molecular. Okay. So in 1943, the great Austrian physicist Erwin Schrödinger was asked by the Dublin Institute for Advanced Studies to deliver a series of lectures on a topic of his choice, and Schrödinger chose the grandiose subject of life as the topic of his lectures. Schrödinger had, of course, been a student in Vienna and had been trained really in the classical physics tradition of people like Boltzmann, and so that really is his physical kind of worldview. He basically is responsible for the wave equation of quantum mechanics, for which he was awarded the Nobel Prize in 1933. He had to leave, he chose to leave Berlin, the Max Planck's former chair, to move to Oxford in, to protest the emergence of, or the emergence of power of National Socialism, and eventually decided to move back to Austria in 1936, which is a really bad idea, of course, because then in 1938 the Anschluss happened, and he was forced to publicly apologize to the Austrian government for having left Berlin, and they didn't buy it, and so he was forced again to leave, and ended up in Dublin, where he lived peacefully for 17 years before returning to Vienna at the end of his life. And it's during this period that he was the head of this Institute for Advanced Studies that was actually modeled on the Institute of Advanced Studies in Princeton, where Einstein was at the time. And so, he was actually asked to deliver a series of lectures, and he chose this topic, What is Life? The subtitle, perhaps more informative, the physical aspects of the living cell. And this is just the poster, very unassuming poster that was circulated. And it was an incredible success. These lectures that happened in February 5th, 12th, and 19th of 1943 were attended by over 400 people, members of the Irish elite institutions and academic communities were there. The Irish Times reported on these lectures, and then eventually, in fact, the lectures were so well attended that people were turned away, and so he had to give those 3 lectures again. So they were actually delivered twice. And then, of course, he chose to present these lectures, write them up as a book, which came out the following year, at the beginning of at the end of 1944, so exactly 75 years ago, published with Cambridge University Press. And this book became a sensation. It very quickly acquired the status of a classic. It was translated to lots of different languages. These are just some examples of the editions that I've been able to find on the web for the book, all these different languages. And it seems to have acquired an incredible reputation for being one of the most important books, scientific books of the 20th century, for having been absolutely crucial, so the story goes, for the development of molecular biology as a science, as a new branch of biology. And so this is incredible, really. It's one of the very few examples that you can find of a book produced by someone not a specialist in the field and the subject of the book, but that ends up having a transformative effect on that discipline, in this case molecular biology. So it's actually really easy to find examples among the founders of molecular biology, or the founding fathers of the molecular biology revolution, basically extolling the virtues of this book, of what is life, and showing how influential this book was for each of them, for their thinking that led to the development of molecular biology as a science. This is an example from Maurice Wilkins. This was something that he said in his Nobel acceptance speech. He said, during the war, I took part in making the atomic bomb. When the war was ending, I, like many others, cast around for a new field of research. Partly on account of the bomb, I had lost some interest in physics. I was therefore very interested when I read Schrödinger's book, What is Life?, and was struck by the concept of a highly complex structure which controlled living processes. Research on such matters seemed more ambitious than solid-state physics, and it encouraged me to move into biology. And this is the sort of narrative that you find, physicists being slightly become disenchanted with what had happened with the Manhattan Project, wanting to enter basically a new field of research, and Schrödinger being responsible for making this new field of research, in this case biology, exciting, and a place where exciting things were about to happen. And so you have James Watson, who has often referred to what is life in autobiographical accounts, saying, when I came back to the University of Chicago, this is in the late 40s, I spotted the tiny book, What is Life? In that little gem, Schrödinger said that the essence of life was the gene. Up until then, I was interested in birds. But then I thought, well, if the gene is the essence of life, I want to know more about it. And that was fateful, because otherwise I would have spent my life studying birds and no one would have heard of me. So that's Watson's reconstruction of his own entry into molecular biology. And there are many other examples. Crick saying, on those who came into the subject just after the war, Schrödinger, What is Life? Seems to have been particularly influential. The book was extremely well written and conveyed in an exciting way the idea that in biology, molecular explanations would not only be extremely important, but also that they were just around the corner. This has been said before, but Schrödinger's book was very timely and attracted people who might otherwise not have entered biology at all. So it's interesting, not just to see the recognition of the book, of the importance of the book for these people, but also which aspects of the book are being underlined. So for Crick, it's the fact that it was well written, the examples I've given before. So Maurice Wilkins is talking about being struck by the concept of a highly complex structure which controlled living process, a structure which controlled living processes. In the case of Watson, is about the gene, the importance of the gene. So it's interesting to see what each of these authors pick up when they are drawing on or referring to Schrödinger. And Gunther Stent, one of the early members of the phage group for Delbruck in Caltech, who actually wrote a lot about the historical development of molecular biology. He said, well, having one of the founding fathers of the new physics put the question, what is life, provided for physicists an authoritative confrontation with a fundamental problem worthy of their mettle. In thus stirring up the passions of his audience, Schrödinger's book became a kind of Uncle Tom's Cabin of the revolution in biology that, when the dust had cleared, left molecular biology as its legacy. So a very, again, clear, unambiguous endorsement of the importance of the book. So you read these accounts and you get the idea that Schrödinger seems to have provided legitimation for this new discipline. You have one of the greatest physicists of the 20th century getting interested in biology, in this new area of biology, in the material basis of heredity, and that seems to have been crucial, really, for the, at least for the narrative, the historical narrative of molecular biology, as has been told by the protagonists of that story. And this is a letter which was unearthed relatively recently, I believe, in the Dublin Institute for Advanced Studies, actually written by Crick to Schrödinger just after the publication of the double helical structure of DNA in Nature in the summer of 1953, saying, "Dear Professor Schrödinger, Watson and I were once discussing how we came to enter the field of molecular biology, and we discovered that we had both been influenced by your little book, What is Life? We thought you might be interested in the enclosed reprints." Of course, these would be the reprints where they presented the double helical structure of DNA. You will see that it looks as though your term aperiodic crystal is going to be a very apt one. So, again, clear endorsement, clear recognition of the importance of Schrödinger's ideas of the gene, material basis of heredity, and in this case, the notion of the aperiodic crystal. So this year is, as I've already mentioned, the 75th anniversary of the publication of the book, and there's been a number of events and publications that have appeared to commemorate the event. There's a paper by Philip Ball in Nature on the book, and there was also an entire conference that was organized in Dublin, Trinity College Dublin, Schrödinger at 75, the future of biology, that brought together a number of world-class scientists, many of them Nobel Prize winning, and the philosopher Daniel Dennett providing the keynote lecture. But what's interesting when you look at these retrospective accounts that have appeared recently is that there's very little engagement with the argument of the book, right? It's sort of odd that a book that seems to have been so influential is hardly ever discussed in terms of what the content that Schrödinger provided in the book, in terms of what the book is about. There's very little really in the retrospective article of Philip Ball, which is of course very nice, but really doesn't engage with the argument that much. And in fact, in all these talks that were organized this year, there was basically nothing really. There was passing mentions to Schrödinger, but it's kind of odd that the conference was titled Schrödinger at 75, and most of the talks were actually not about the book at all or about the influence of the book, but rather about the future of biology, the development of biology, or what biology, what new developments may come. So that's kind of odd. And if you look back at the 50th anniversary, there was another meeting that was organized in Dublin with an formidable roster of authors: Stephen Jay Gould, Maynard Smith, Lewis Wolpert, Stuart Kauffman, Roger Penrose. So really first-class roster of speakers. But again, one is sort of disappointed when one looks at the book that came out of this meeting. It came out 25 years ago with Cambridge University Press. What is life the next 50 years? And again, there's very little engagement with the argument. Kauffman is perhaps the only exception to this. So it's odd, right, that this book, often when it's discussed, you either find people discussing the question, what is life, or discussing the future, the future of biology. In both cases, in fact, the subtitle is a reference to the future rather than an engagement with the arguments of Schrödinger himself. So I think there's something that's still missing in that respect, and that's what I set out to do in looking at this book, trying to really go back to the book and really look in detail at what were the arguments that Schrödinger wanted to put forward, and engage the adequacy of these arguments and also the impact that they may have had on the development of molecular biology. So let's go back to the book. I mean, it's a short book. It's under 100 pages, and it's one of these books that it's very convenient because they include these analytical table of contents that provides not just the titles of the chapters, but also the sort of summary, the summary of the argument in each of these chapters. So that's the book, the 7 chapters. So what is it that one knows? I mean, if you ask any biologist or any philosopher of biology or historian of biology, what can you tell me about Schrödinger's What is Life? You're likely to hear one of 3 things, or a combination of 3 claims that are very well known. Okay, the first one is the idea that the hereditary substance, I use the term hereditary substance rather than DNA because DNA at the time hadn't yet been conclusively demonstrated as the carrier of genetic information. Avery's experiment is actually from the same year, 1943. Schrödinger believed it was proteins. In fact, most geneticists at the time believed that proteins were the carriers of genetic information, so I talk about hereditary material instead of DNA in that respect. The claim that Schrödinger makes is that this hereditary substance is an aperiodic crystal that contains a code script for development. Okay. The second claim that people might have heard of that Schrödinger makes in the book is that organisms feed on negative entropy. This is a term that Schrödinger uses to comply with the second law of thermodynamics, to resolve the seeming anomaly of how organisms conform to the second law of thermodynamics. And finally, the idea that the study of living matter is likely to prompt the discovery of new laws of physics So that the study of life will lead to the formulation of discovery of new laws of physics. Okay, so these are the three sort of lessons, take-home lessons of the book that you might have heard. But when you look at the book, again, what's interesting is that Schrödinger doesn't give each of these claims the same amount of time. In fact, most of the book is actually centered on the development and the formulation of that first claim. So actually, the second claim, so actually I should say most of the book is actually making this case, I'll explain in a moment. The second claim about negentropy and thermodynamics is actually confined to a part of one single chapter, chapter 6, order, disorder, and entropy. But again, it's kind of odd because that engagement with thermodynamics that Schrödinger provides, even though it's well known, is not very obviously connected to the argument that Schrödinger presents in the rest of the book. In fact, Schrödinger himself says on pages 73, 79, so it's only really 6 pages that we're talking about, I will try to sketch the bearing of the entropy principle in the large-scale behavior of a living organism. And then he says, forgetting at the moment all that is known about chromosomes, inheritance, and so on. So he's actively, basically, dissociating his discussion of thermodynamics from his more broad discussion about genetics and heredity, which I will come to in a moment. So that's interesting. It's even more interesting to find that third claim about the new laws of physics is actually confined to a single section of the final chapter. So it's even more restricted, where he says, living matter, while not eluding the laws of physics as established up to date, is likely to involve other laws of physics hitherto unknown, which, however, once they have been revealed, will form just as integral part of this science as the former. Okay, so there's this sort of prediction that Schrödinger makes, which people picked up on and tended to continually refer to Schrödinger, in the early years, in the 1960s, 1950s, 1960s. So I think it's important then to focus on that first claim and understand what is it that Schrödinger is trying to say. What is the argument? Well, the argument really has to do with biological order. The book is called What is Life, but it doesn't really discuss life in general. It's actually an analysis of the origin and nature of biological order. So that's really the question that Schrödinger is trying to address in the book. Okay? And in order to address this question, he's a physicist, and so he acknowledges his knowledge of biology is quite limited. And so he begins by examining in the first chapter, what is the nature of order in physics? And so the chapter is called The Classical Physicist Approach to the subject being order, okay? So if you asked a physicist, what would a physicist tell you about the nature of order, okay? And what he says is that in physics, and of course here he's drawing on this statistical mechanics tradition that he feels he considers to be descendant of or developing, that physics tells us that atoms are incapable of exhibiting orderly behavior because they are subject to the stochastic effects of thermal agitation at any temperature above absolute zero, right? So at any temperature above, basically, if there's temperature, there's thermal agitation, Brownian motion, and what that means is that individual particles or molecules exhibit this sort of random stochastic movement that is disorderly, okay? So there is no order at the molecular level, according to Schrödinger. What you really have is order at the collective level. When you have large ensembles of particles, molecules, you then there find that you can make predictions. You can identify statistical regularities. The laws of physics, according to Schrödinger, are statistical in nature. So that's what he says. Order and regularity can only emerge upon consideration of huge numbers of atoms, molecules, particles, which collectively display macroscopic patterns of order as described by the law of large numbers. Okay? So the larger the number of particles that you're considering, the more accurate your predictions can be of what will happen to that ensemble, that collection of particles. Okay? So he calls this order from disorder. Right? Why order from disorder? Because you've got disorder at the macroscopic level, but when you consider all of these disorderly molecules together, you can identify orderly behaviors. Right? So that's what he says, that's what Schrödinger says is the case in physics. And he gives a number of examples. And of course, this is really drawing on that Boltzmannian tradition that was so important to Schrödinger. So he gives a number of examples. He asks the reader to consider a flask or a beaker with smoke particles. And he says, well, you know, if you look at the smoke, the fog collectively, you know that it will eventually move in one direction. But if you are looking at the trajectory of an individual particle, you can see that it's really, really stochastic. You can't know exactly where it's going to go. Right? So it's an example of, if you look at individual molecules, you don't know what's going to happen. If you look at collective, large numbers of molecules, you can. And he gives other examples. Diffusion, from left to right in a solution of varying concentration. You don't know what each particle, where it's going to go, but you know what's going to happen collectively. And other examples, the other example he gives is paramagnetism, the orientation of particles. Again, one can't tell what an individual particle is going to do, but collectively one can make very accurate predictions. And of course, this is part of the sort of statistical revolution that took place in the 19th century that led to transformation really of physics through statistical thermodynamics and many other areas, of course, of knowledge and economics. You know, statistical methods become very important, and what they provide is a way of making predictions without knowing what the individual units are doing. Okay? And this idea is really, really important for Schrödinger. So here is where things get interesting, okay? Because he says, well, knowing what we know about physics, what I just described, you would expect a physicist, he says, a naive physicist might think it's just obvious, you know, not even worth making the case, that the order of life would have to be similarly based on law-like patterns of behavior exhibited by large ensembles of molecules. Because, of course, an organism, a cell, is far more ordered than a smoke fog. So, obviously, you would expect then, he says, for there to be many of these examples of order from disorder processes going on. But then he says, no. That's not only is it not obvious, but it's wrong. Okay? So at the beginning of chapter 2, you have this twist. He says, well, the classical physicist expectation, the expectation of order from disorder, far from being trivial, actually is wrong. Okay? So why? Why did he say this? Well, he says this because he is reading genetics literature, and he reads and finds that what the genetic literature is telling us, genetic literature in this period, that the order of an organism is essentially determined by its genes. Everything that exhibits orderly behavior at the cellular organismic level has its basis in the genes, right? And then he says, well, we know from experimental evidence, X-ray studies, that the gene molecule only has about a few thousand atoms. And then he says, well, this number, a few thousand atoms, is much too small from the law of large numbers point of view to entail an orderly and lawful behavior according to statistical physics. So it seems to contradict, in a way, what we know in statistical physics, because you have a single molecule, a small molecule, being responsible for generating order. In fact, he says genes are so small that a physicist would assume that they should not be able to reliably code for heritable traits, because they are likely to be prone to stochasticity, to thermal agitation, to Brownian motion. But we know for a fact that that is not the case. You know, that in fact it is the case that Schrödinger says you got these molecular determinants of macroscopic order in the biological world. He says genes are remarkably stable, he says, with a durability or permanence that borders upon the miraculous. Right? So how is it possible that a molecule, the hereditary material, being a molecule, and so being small and being subject to thermal agitation, how can it be at the same time so permanent, so rigid, and so fixed to be able to give rise to the patterns of order that we find in development and in biology more generally? So really, this question is, this paradox is what Schrödinger is essentially trying to resolve in the book. Okay? Unfortunately, this is not always discussed in the literature, which is why I think it's very important to look at the argument, because this is basically what the book is about. Most of the book is about resolving this seeming contradiction of the expectation that a physicist is going to have, trained in statistical mechanics, and what genetics seems to be telling us. Okay? So Schrödinger is a very lively writer, and he gives us as an example of the permanence of genes the Habsburg lip. As a good Viennese, he talks about the Habsburg royal family, and he says, well, if you look at all these Habsburg kings over the centuries, they all display this anomaly in the jaw, in the lip. And you find that from the 16th century all the way to the 19th century, right? And so these are just some examples of Habsburg monarchs. And he says, well, I mean, this is really, really puzzling because this anomaly has a genetic basis. We know it's a genetic trait. And so if it's a genetic basis, we're talking about a molecule that is being responsible for this trait. And so how can a molecule be so incredibly permanent to withstand not just, minutes or hours, but centuries, given that you can find it over the centuries, right? So this is just an example of an illustration, really, of this paradox that Schrödinger is trying to resolve in the book, okay? How do we reconcile the small size of genes with extraordinary stability in the face of constant stochastic perturbations? Okay, so what does he do? He uses his incredible intellectual powers to find a way to resolve this paradox. And what he says is, okay, right, the genetic material, Schrödinger says, must have the rigid solid state structure of a crystal, he says. Why a crystal? Because a crystal, he says, has the sufficient stability of a solid to be able to withstand the thermal agitation that would otherwise plague it, right? So the genetic material has to be some sort of crystal. He calls it a germ of a solid, the beginning of a solid, because of course a single molecule can't be a solid. So he says, okay, so it has to be a crystal with covalent bonds, and these bonds provide the molecule with the stability necessary to withstand thermal agitation. But it's not just any solid or any crystal. It can't be a periodic crystal with a seemingly sort of periodic lattice, because it needs to, in some way, specify the code script, what he calls the code script for the organization, right? So the order has to be in some way specified by this crystal, and so he says, okay, so the only way I can think that this happens is that this crystal is aperiodic. All the monomers that make it up are slightly different, and in that way, the information doesn't talk about information, but he says, that way, this crystal can, in some way, he says, encode that order that then is going to be amplified at the macroscopic level, okay? So that's where the aperiodic crystal notion comes from, okay? It's an attempt by Schrödinger to resolve this question of size, really. It's a question of scale in the end. And he says, this means that in biology we have a totally different understanding of order than the one that we have in physics. So in the first chapter, I just already told you, it's order from disorder that Schrödinger thinks legislates the physical world. In biology, given that we have this situation, we have what he calls order from order. The from here is slightly ambiguous. Some authors, commentators have thought, well, it's a temporal thing, but I think it really refers to different scales. So macroscopic order from microscopic order versus macroscopic order from microscopic disorder. So what's really interesting is that the only other example Schrödinger can think of, because he says the order from order principle is not alien to physics, you also find it in physics, but not in natural systems, but in artifacts, in machines. Because in machines you also have a design that specifies macroscopic order. It's a large solid state structure that, because of its size, can withstand the disruptive effects of thermal agitation. And so he says that in the end, this is the conclusion of the book, that the clue to the understanding of life is that it is based on a pure mechanism, a clockwork that also hinges upon a solid. The aperiodic crystal forming the hereditary substance largely withdrawn from the disorder of heat motion. Okay? So that's basically my reconstruction of the argument that Schrödinger puts forward in What is Life? Okay, so let's now look critically back at these ideas and see what we make of them. What should we make of these notions of order from order, order from disorder, with the benefit of 75 years of research? Well, okay, order from order first. It seems quite evident that there's something true about this, that Schrödinger effectively anticipated something very important that was later developed and consolidated in molecular biology, which is the transmission of biological order from a hereditary code script. Now, what's problematic is that very often people consider this code script that Schrödinger talks about, a code script for development, as being anticipating the notion of the genetic code, right? But actually, this is kind of problematic, because if you read closely the text, what you find is that there's no discussion of a sort of translation of a message, which of course is what a code entails, a code understood as a cipher. But rather, Schrödinger is talking about the code script as a sort of plan for development, the way we talk about the highway code when you're learning to drive. The sort of rules that are responsible, that explain the norms of behavior, as it were. And it seems that this is really what Schrödinger seems to have in mind when he talks about a code script. And so the attribution to Schrödinger of anticipating the genetic code seems to be kind of problematic in that respect. I think that instead of having anticipated the notion of the genetic code, this notion of a translation of a message, which Schrödinger that doesn't talk about translating some sort of DNA from RNA or DNA to RNA, RNA to protein. What you really seem to find when you look at the text is the anticipation of the notion of a genetic program. I mean, this is the way I read the text. And of course, what that means is that the ideas that Schrödinger puts forward with regards to this code script are subject to the same problems that are known to plague the genetic program notion of development. So in earlier work, I examined this genetic program model of development, the idea that you have a software basically encoded in the genome that then is executed. There's a sort of algorithmic set of instructions that are executed that lead to the production of the organism. That idea is, of course, quite problematic. I mean, it was originally sort of proposed by Jacob and Monod and also independently by Ernst Mayr in 1961 and became the really central notion for developmental genetics. But over the course of the last 20 years, there's been a lot of criticism. And so in my critical reconstruction of this notion, I suggest that the notion of genetic program is problematic for three reasons. One is that it advocates this neo-preformationist view that developmental information is in some way already encoded in the genes, and which I think is a very common way of talking about DNA even today. And of course, that's a very problematic notion. The idea that all the information necessary for development is already found in the DNA. Secondly, this notion of genetic animism, what I call genetic animism, which is the attribution of agency and powers to genes. When we talk about genes doing things, self-replicating, directing, controlling development, that's a very problematic notion. And yet, it seems to be very, very central to this notion of the genetic program. And finally, the idea that if you have a program for development, it means that you can compute the outcome of development if you know all the initial conditions. A number of prominent molecular biologists and developmental biologists have suggested this, including Sidney Brenner, Lewis Wolpert. The idea that complete knowledge of how genes interact during development will enable us to compute the embryo. In fact, Wolpert's contribution to the 1994 volume on the 50-year retrospective of what it's like is actually called "Can We Compute the Embryo?" So Wolpert himself is attributing to Schrödinger this notion. Now you may be thinking, this seems like really far-fetched. I mean, how can you attribute all of this to poor Schrödinger? Well, if you look at how Schrödinger uses the notion of the code script, you can actually find it being used to defend each of these three claims that I've just made, right? So when Schrödinger says that the chromosomes contained the code script for the entire pattern of the individual's future development and its functioning in the mature state, or when he says that the code corresponds to a highly complicated specified plan of development, he's essentially advocating this neo-preformationist view that then you can attribute to the genetic program literature. When he talks about the chromosome structures being not just low code, but also an executive power, so not just architect's plan, but also builder's craft, what he's essentially doing again is he's attributing to that molecule agency. the agency to begin to initiate and to control and to regulate the developmental process. That's in the text, that's in What is Life. And finally, Schrödinger also seems to anticipate this notion of developmental computability. He says, in calling the structure of the chromosome fibers a code script, we mean that the all-penetrating mind, one conceived by Laplace, this is sometimes referred to as Laplace's demon, to which every causal connection lay immediately open, could tell from their structure whether the egg would develop into a black cock or a speckled hen, into a fly or a maize, a plant, a rhododendron, a beetle, a mouse, or a woman. Right? So he's attributing to the code script basically all the information required for an all-penetrating mind who knew, that would know all the initial conditions to determine, basically, to determine what would be the outcome of that developmental process, right? So I think it's quite apparent then that in the book itself you can already see anticipating magnificently, really, impressively, 20, 30 years before, in advance, this notion that would then become so dominant in developmental genetics. So, of course, this is problematic. But having said that, Schrödinger was, of course, right in that there is an order from order principle at work in morphogenesis, and that it's intimately connected with the hereditary substance, right? So there is a sort of causal linearity from DNA to RNA to protein, even if there are some exceptions to that sort of central dogma of molecular biology. Schrödinger was right on, this has to be, of course, recognized that even before, DNA was identified as the carrier of information, that Schrödinger had anticipated that there would be a need to talk about that this transmission of order from one set of molecules to another. But, as I've just indicated, he was wrong to localize in this substance, in what would then later become identified as DNA, all the information required to specify the organism, and he was even more wrong to invest it with the causal power to initiate, control, and direct development. And as I've already mentioned, a number of biologists and philosophers of biology have really provided systematic critiques of these ideas. One example is this book that I like by Lenny Moss, What Genes Can't Do. And also there's another problem with when we think about this order from order principle, which is that order that Schrödinger talks about is not exclusively passed on by the DNA. The hereditary material of the chromosome is really not the only repository of order that is then transmitted. Of course, we have epigenetic means of inheritance, and this has been a very lively and important field of research over the past 25 years. This is a very nice book by Jablonka and Lamb from 2005, I believe, called Evolution in Four Dimensions, that shows the importance of epigenetic inheritance, and there's been, of course, more recent studies as well showing that. So that's all I want to say about the order from order principle. When we look back at it 75 years later, what about the order from disorder principle? Well, of course, from a physical perspective, it's correct. Right? So as far as physics, the physical world is concerned, it's correct to say that the principle reflects the transformation of physical law that was brought about by the sort of by Boltzmann and Gibbs' development of statistical mechanics. What's more problematic is in the claim that Schrödinger develops, that he makes, that this principle that is so important to physics has no role to play in biology. Remember, that's the sort of twist in the argument that I mentioned at the beginning. That seems to be sort of problematic, to say that there is no order from disorder in biology. In fact, if you think about it, order from disorder regularities expressed by statistical laws are everywhere in biology. It's just simply not true that biology has a sort of totally different sort of mechanism through which order is produced. I mean, just think of Darwin's theory of evolution or Mendel's principle of inheritance. They're both statistical regularities, as is the population genetics that brought them together, in the sense that knowledge of individuals is derived from the study of large populations, right? So this seems sort of obvious. And yet, no one has actually mentioned this. in the vast literature on the book, no one has noticed that the separation between order from order and order from disorder that Schrödinger takes to be so important to separate physics from biology just doesn't have collapses when you consider genetics or you consider evolutionary theory. Fisher, one of the founders of theoretical population genetics, himself considered himself to be a sort of the Boltzmann of biology. He's been referred to in the secondary literature by Dupuy and Weber in Darwinism Evolving as the Boltzmann of a blade of grass. This is a paraphrasing of the idea that Darwin became the Newton of the blade of grass. In a sense, what this means essentially is that Fisher was trying to do for biology what Boltzmann did for physics, very explicitly, right? So it seems very odd to want to say that the Boltzmannian view of order plays no role in biology. Because especially, we're talking about genetics, we're not even talking about another very distant branch of biology. And, that's really in terms of, it's problematic when you think of the idea of order emerging from disorder and applying that not really to gas particles or molecules, but rather to individual genes or individual organisms, zebras, in a population of zebras. But even statistical mechanics itself seems to have a role to play in biology. A number of authors have suggested that much. Brian Goodwin explicitly wrote this paper to make the case, and more recently there's been a number of interesting papers essentially trying to use statistical mechanics and the conceptual apparatus of statistical mechanics to make sense of development, of cell differentiation, right? And so it seems completely wrong to want to say that order from disorder plays no role in biology. And so that's in terms of the traditional understanding of order from disorder coming from statistics. But of course, there is another way of thinking about order from disorder, which is self-organization. Okay, so self-organization really explains the phenomenon of self-organization, explains how macroscopic order emerges from disorder, right? And so this is a real example, really a very important counterexample, perhaps, of what Schrödinger is saying. And of course, you've got these far from equilibrium dissipative structures in physics. Just think of whirlpools or tornadoes or hurricanes or these Bernard cells and sort of chemical reactions that display patterns of order. But of course, organisms themselves, living entities, living systems are also self-organizing dissipative structures. So if that's the case, then that's another serious problem for the idea that order from disorder plays no role in biology, because organisms themselves are enacting that very process of self-organization. And there's a lot of interesting work has been done recently to show that not only is the cell a self-organizing entity, but a number of organelles in the cell are similarly self-organizing, like the mitotic spindle, the Golgi apparatus, cell nucleus. So these are all examples really of what Schrödinger thought was basically absent in the cell. Now, what's interesting is that Schrödinger seems to have come close to the idea of self-organization in his discussion of thermodynamics, because when he discusses thermodynamics, he's actually saying, well, organisms maintain themselves alive by taking in matter and energy from the environment, by metabolizing, right? And he talks in those terms, but he just doesn't occur to him that need that organisms exhibit of having to take in matter and energy from the environment to maintain themselves in a steady state far from equilibrium constitutes an example of order from disorder. It just doesn't occur to him. But I think this is an important aspect of any retrospective analysis of this notion of order from disorder in biology. There are a number of other examples in the cell, really, of how order emerges from the coupling of disorderly or chaotic reactions. This is the Brownian-Ratchet model of motor-driven transport. You don't need to worry about the details, but the important point here is that you have two chaotic processes, which are the random walk to which the protein that's represented in a circle is exposed to, and the synthesis or the hydrolysis of ATP together lead to an orderly outcome. Because what you have here is sort of movement in one direction by the harnessing of Brownian motion, okay? You can ask me about this in more detail in the question period, but basically this is just an example of how order from disorder emerges. In fact, it's discussed in these terms. If you look at books, that are, have been written on these sorts of processes in biology, actually, you have very clearly the idea that order is extracted from chaos, right? So again, this seems to be very problematic for if one wants to uphold Schrödinger's view of cellular order. Okay, so what I want to suggest now, or what I want to look at now, is the legacy of the ideas of Schrödinger. Okay, having provided you with the argument that Schrödinger puts forward and what I take to be how those ideas have stood the test of time. Now I want to talk a little bit more about the legacy of these ideas. Okay. So if you recall from what I've said before, the argument that Schrödinger puts forward is that the source of all cellular order is in the fixed solid-state crystal structure of the genetic material, which renders it impervious to stochastic forces. Okay, that's the claim. I should probably say that if you look at the secondary literature, the way historians talk about the impact of the book, they often say, well, the claims that I mentioned at the beginning, Crick and Wilkins and Watson, actually were put forward decades after the publication of the book, and that there seems to have been a desire to legitimate molecular biology by invoking the name of Schrödinger. And so historians have tended to say, well, we shouldn't take scientists too seriously when they make these retrospective evaluations, when Watson talks about the fact that he would have been, no one would have heard of him because he would have been looking at birds unless he had read Schrödinger. But I think, so for that reason, often historians, and this seems to be the consensus even today, that Schrödinger's book really wasn't that influential for its content, but rather because it was used as a sort of argument from authority, many years after the fact. What I want to suggest is that if you actually pay attention to the argument that Schrödinger puts forward, you can make a case for the book having had an important influence on the development of molecular biology. So it's not just the case that this book was used in the 1960s, 15 years later, to basically legitimate molecular biology using this great physicist, but that if you look at the arguments that Schrödinger put forward, there's something to those arguments about order, which are problematic, as I've just explained, that you can find, that you can see in the development of molecular biology in the latter half of the 20th century. So this is the claim that I've already explained is the basis of the thesis that Schrödinger puts forward in the book. Now, think about it. Think about what it means. What are the implications of that claim? Well, the implications are that the order that Schrödinger says is encoded in the aperiodic crystal must somehow be reliably transmitted to the rest of the cell's components, especially to the proteins, so that these can individually express it through their functions in a way that similarly eludes or overcomes the raging Brownian storm of the molecular real, right? So if Schrödinger is saying, molecules, DNA or the hereditary material is too small to exhibit order, and consequently it has to have this really rigid and fixed structure, it follows that when that order is transmitted to other molecules in the cell, these other molecules also have to have this rigid, fixed structure for them to be able to perform their function, to pass on and amplify that order without being subject to Brownian motion. I think that just follows from the argument, even though Schrödinger doesn't say that explicitly. And so what I think happened, and this is my hypothesis, as a working hypothesis, that the influence of this idea, this one, granted molecular biologists the license to dismiss the effects of stochasticity on subcellular processes. You don't have to worry about stochasticity anymore, because what's important is to account for that rigidity and fixity of the molecules. So forget about stochasticity. Allowing them to focus on the structure of macromolecules, drawing attention to the crystal-like rigidity, emphasizing the functional specificity, and ignoring the destabilizing influences of the microscopic environment. Okay, so what I want to suggest is that, this idea, so that Schrödinger exerted a very important influence on the development of molecular biology, which has to do with the notion of cellular order that molecular biologists implicitly have over the course of basically the second half of the 20th century. What idea of order? The idea of order from order where you have fixity and rigidity as the fundamental properties of molecules, okay? Where you can forget about Brownian motion, even though it's inevitable to think about Brownian motion at the molecular level. You can forget about it because these molecules have to be, they need to be rigid and fixed, because otherwise there will be no order in the cell, okay? If you think about it, that's the way we think about proteins and macromolecules in molecular biology, you know? So what I'm trying to do here is connect that notion that is kind of familiar to a contemporary molecular biologist with the argument that Schrödinger puts forward in 1944. Okay, now you may think again, wow, this is really far-fetched. I mean, how can you attribute to Schrödinger these ideas? I mean, surely this is very, very speculative. Well, okay, it's speculative, but I think that you can find, if you know where to look, you can find evidence for this sort of attribution of responsibility. And a place where I have looked and I have found evidence for this claim is in the work of Jacques Monod, who's of course one of the founding fathers, intellectual figures in early molecular biology. And what's interesting about Monod is that he actually changed his mind about the nature of biological order as a consequence of having read Schrödinger. Reading What is Life led Monod in the 1950s to shift from a statistical and non-deterministic view of biological regularities, which he expresses in his very early work, to one that reflects a static clockwork position that really is instantiating that Schrödingerian view of the cell. And you can actually find this if you look at his work in the 1950s. He says in 1957, the whole trend of modern molecular biology makes it every day clearer that structural stability and rigidity, rather than dynamicity, okay, are the most essential characteristic properties of cellular macromolecules. He even says, and this comes from a lecture that was, never published. These are from his lecture notes, you can find in the archives. He says, Schrödinger, with the insight of genius, Monod writes, had perceived this as a necessary attribute of the hereditary material. The validity of this view is now beautifully demonstrated for DNA. But stability and rigidity are apparently not just limited to DNA. Recent work shows conclusively that the bulk of cellular high molecular RNA is stable and non-dynamic, and the same, as we have just seen, is true of protein. Okay? So you have here basically the claim that I've suggested with regards to Schrödinger's influence on how molecular biologists think about order in the cell. He even talks about, he discusses a number of examples in this lecture. He talks about the ribosome, and he says this protein synthesizing process appears to work with a very high precision. And the concept of molecular microheterogeneity, which of course is a reference to of noise, really, of stochasticity, due to errors or fluctuations in this process appears unwarranted. We don't need to worry about that. Putting it otherwise, even in the formation of such a very large and complex molecule, even when we're making a protein, okay, the synthesizing system, the ribosome, appears to work mechanically, Monod writes, like a clock or a precision machine tool rather than statistically. And then he writes to himself, like what? And then he writes also Schrödinger. So, interestingly there, Monod is drawing this distinction, right, between statistical order and mechanical order. And he's actually saying, well, Schrödinger was right, that the order at the molecular level is mechanical and not statistical. So this is, I think, very, very telling, very, very revealing, especially because if you look at the contemporary literature today, what you find are characterizations of the ribosome of protein synthesis which are exactly the opposite of this view. So what you find today are people writing papers arguing that we shouldn't think about the ribosome as a precision machine tool or a clock, and that we shouldn't think about the process as being mechanical at all. An example of this is this paper by Peter Moore from 2012 called How Should We Think About the Ribosome, where he's saying, that ribosome, the idea that ribosome works like a clock or a machine tool here for making candy bars is completely wrong. We shouldn't think about macromolecules as molecular machines. The use of the word machine in this context is pernicious because of the implication that the functional properties of macromolecules can be explained mechanically, which is simply not true. Okay? So what you have is half a century later, we are having to rethink this idea. I mean, it is necessary to make this claim. And if it is necessary to make the claim, it's because Monod's notion, has basically remained dominant to this day. And this is why we seem to have a proliferation of articles and review papers, research and review papers being published, making the case that we should not think about the order at the molecular level as being mechanical. Okay? So the contrast here couldn't be greater between these two. And if you think again more broadly about this idea of fixity and rigidity, it explains a lot. It explains why molecular biologists and developmental biologists like to use these sorts of representations when they think about protein-protein interactions, or about gene regulation, or about metabolism. Right? This is an example of the work that was done by Eric Davidson and his collaborators in understanding the regulatory network in the cell. And it's not a coincidence that these sort of diagrams are reflecting the nature of electronic circuits. Why? Because for these people, they are of the same sort of nature. They are fixed, solid state circuits. Which, of course, is a very problematic way of thinking about what's going on in the cell, because molecules are not fixed. They are, in fact, subject to thermal agitation, to Brownian motion, and so these sort of idealized representations are extremely problematic. And the same thing goes for how we represent metabolism. Again, these are just classic examples that you can find in textbooks and in posters, often in biology faculties. I don't know if there's one here, but these are very, very frequent representations. And again, these sort of representations are implying a view of the nature of cellular order, which Schrödinger originally proposed, and the people like Monod championed. A view of cellular order where everything has to be fixed and rigid to be able to have that macroscopic order. And of course, the problem is that you don't really have physical wiring connecting molecules in a cell as you do in an electronic circuit. And that when you actually look at the individual molecules and you actually examine the empirical literature on the extent of the number of interactions that each of these molecules, each of these proteins engage in, you end up with these sort of impossibly complicated diagrams, right? Where you have the black arrows representing the sort of textbook example or the textbook characterization of molecular pathways, and all these crosstalks being what you actually find empirically, experimentally, right? The reality basically leads us to transforming our view from this very neat picture to this really messy one. And the reason why one reason I would suggest why we're so comfortable and with these sort of representations is, I think, because of how molecular biology has understood the nature of biological order. Okay, and in trying to understand why biologists think in this way, I think that looking at Schrödinger's arguments in What is Life can give us a clue to why it is that so many biologists feel comfortable with this idea of fixity. And I just want to mention, if you're interested, I have, I think there's one of the papers that Paco mentioned, published recently, called Is the Cell Really a Machine?, where I discuss these examples in more detail. I don't go into any historical speculations. I don't mention Schrödinger. But basically, it was this kind of work that I was doing when I was reading the literature, and I was discovering that there's this sort of, tension between this traditional mechanical view and this more recent view that's advocating stochasticity, that made me want to find out why did we have this mechanical view in the first place to begin with. And there, I think, is where Schrödinger may have something to answer for. Okay, so I just want to, in this final part of the talk, maybe address a question that you may have been thinking for a while, is like, am I being fair to Schrödinger? At the end of the day, Schrödinger was a physicist, didn't know much biology, and he gave these lectures in 1943. So to what extent is it fair to blame him for this understanding of order? What I want to suggest is that we should blame Schrödinger. Okay, that there is no reason to be shy, and I'm going to try to tell you why I think one can make a case. So in this talk, I have presented three retrospective criticisms of what is life. Okay, the first one was this genocentrism, which has to do with how Schrödinger understood order from order. Okay, the idea that the hereditary material is responsible for all macroscopic order. I've also criticized him for denying that order from disorder principles play any role in biology. Okay, I've also said that. And I have also suggested that Schrödinger is some way responsible for the dismissal of stochasticity. Okay, now you may be asking, is this blaming Schrödinger for not knowing the future? Are they unfair criticisms posed with the benefit of hindsight? Is it only that now we realize that these claims are problematic? Only now that we think that genocentrism is a problem, that order from disorder plays a role, and that stochasticity should not be dismissed? No. None of these claims were inevitable, historically speaking. And here is where sort of the historical work gets really interesting, because if you look at how the conditions and how Schrödinger actually came to write the book and prepare the lectures, what you find is that these claims, all of these claims, represent deliberate choices on the part of Schrödinger. They were not inevitable. In fact, Schrödinger is choosing to side with biologists that advocate genocentrism and choosing to make these claims, okay? And that makes it even more interesting, because there you have there's something going on here. You know, Schrödinger seems to have certain motives for arguing the way he does. And so here we need to look, as I say, into the historical conditions that led to the generation of the lectures, the production of the lectures of What is Life. And so what I want to suggest here, again, this is a hypothesis that really hasn't been really properly considered in the historical literature, that the only way to understand what is life is to think of it in the context of the debates that Schrödinger was involved in physics with other physicists. And only that way can we understand why Schrödinger argues the way he does in biology. Okay? So what I want to suggest is that Schrödinger's What is Life constitutes his attempt to salvage this mechanistic, reductionistic, deterministic worldview of classical physics that he had been brought up with, that had become undermined by the conventional Copenhagen interpretation of quantum mechanics, a science that he himself had helped to create. So there's an incredible irony here, okay, that maybe Schrödinger was responsible through his work of undermining the worldview that he wanted to defend. Okay, and this is what I want to suggest. So, take genocentrism, okay, that I've discussed in so much detail earlier when I talked about order from order. This genocentrism that pervades Schrödinger's biological views was actually not the orthodox view in genetics at the time, in the 1930s and early 1940s, but rather reflects the sources that Schrödinger chose to read in preparation for his lectures. The kind of articles that Schrödinger chose to read to inform himself about the state of the art in genetics. And what you find if you look at the archives is that really early on, I mean more than a decade before he prepared his lectures, Schrödinger had been corresponding with Karl and Hans Pribram in Vienna about the role of Brownian motion and the nature of the gene. He had been already interested in 1932 on how, on biological questions. And he had actually been prompted to look at these, these issues as a consequence of having read this paper by Pascal Jordan, one of the, again, founders or early quantum theorists of quantum mechanics, who worked with Bohr, where Jordan tried to provide a sort of quantum mechanical foundation for biology. Okay, and Schrödinger actually was appalled by what Jordan was suggesting. So maybe I should say something about this. So, of course, Schrödinger is engaged in a very long debate with Niels Bohr and his students on the interpretation of quantum mechanics. Okay, because Bohr and Heisenberg conclude that the findings of quantum mechanics show that there is indeterminism at an ontological level, okay? That there is, that you have this uncertainty principle where you, and this complementarity principle that suggests that the observer plays a role in the on the state of the entity that is being characterized. So there's a sort of strange situation happening where you have ontological indeterminacy at the microscopic level, And Schrödinger was actually never happy with this interpretation that came to be known as the Copenhagen interpretation, because Bohr was based in Copenhagen. And so for his own wave equation was interpreted in this probabilistic sense. And so Schrödinger, already unhappy with the consensus view, the consensus interpretation of quantum mechanics, which is this Copenhagen interpretation, becomes even more unhappy when he discovers that one of Bohr's students is suggesting that this indeterminacy that is rife in nature, in the physical world, also is a foundation for biology. He becomes livid. And so he says this in his letters to the Pribram brothers. And so they respond to Schrödinger, says, "My brother and I are very pleased to have you as a confederate in the struggle against all occult forces," because Jordan is here in this paper suggesting that organisms serve as amplifiers of quantum effects. That's what he says. So it's not order from order, it's not even order from disorder, it's actually disorder from disorder. Okay, the idea here is that organisms in their seemingly stochastic behavior are basically amplifying the effects that you already find in the quantum world. Okay, so it's not an amplification of order, it's an amplification of disorder. Okay, and this to Schrödinger and to the Pribram brothers seems to be mystical, almost vitalistic. Okay, but Jordan seems to, he actually develops this program. He coins the notion of quantum biology. And he thinks that biology will follow suit from physics as a science that will embrace this indeterminism. And of course, Schrödinger doesn't want that. Schrödinger wants to defend determinism, right? So he says, well, what should I do? And so the brothers suggest to him, you should write a reply to Jordan. This is in 1932. And then they also say, well, look, you should look at a number of papers that may help you in preparing this response to Jordan in biology, given that you don't know much biology. And they suggest that he should read this paper that is sort of reductionist in its style, Quanta in Biology by Hans Pribram. And more importantly, this very provocative paper by Hermann J. Müller called "The Gene as the Basis of Life." Okay, what you find is that Schrödinger becomes completely engrossed by reading these papers, and this provides the knowledge of genetics that Schrödinger then uses for his lectures 10 years later. Okay. In fact, what you find in this paper is the most incredibly reductionistic manifesto. If you think Dawkins is bad talking about the selfish gene, you should read this paper from 1929, where the gene is basically responsible for everything. It's responsible for the order in the cell. It's responsible for life itself. Right? The great bulk, at least, of the protoplasm was only a byproduct originally of the action of the gene material. This is a quotation from the paper. Everything that we need to worry about in the cellular level can be traced all the way back to genes, okay? And in fact, you can find in the archive Schrödinger making notes on the basis of this paper, which of course is not actually referred to in the What is Life lectures, but provides the foundation for the genetics knowledge that Schrödinger draws upon to make his case. And that's why it's so genocentric, because he's reading this kind of work. He's not reading even Morgan himself was still ambivalent about the materiality of the gene or about the causal supremacy of the gene. He's reading other authors that are completely committed to a more reductionistic and genocentric view. Then there's another interesting situation when you look at the book, which is that much of the argument is drawing on a paper by Max Delbruck and Carl Zimmer and Timofey Wrzoski, a paper that was published in a journal that folded after 2 issues, that is not well known. It was actually referred to as the green pamphlet because of the preprint came in these green covers. And much of what Schrödinger says about the stability of the gene is drawing on this paper published in 1935 by Delbruck and others. And what's interesting again is that even this paper, okay, which is so important, this is actually the reason why Delbruck initially becomes well known, is through the popularization through Schrödinger of this paper. What you find when you read this paper is that it doesn't support the view of order and of the importance of genes that Schrödinger defends. So Schrödinger is relying on this paper, but at the same time, he's distorting and changing the conclusions of this paper, which is actually really interesting. This paper actually, at the end of the paper, it provides a model of the stability of the gene, which of course is the argument that Schrödinger develops. And the authors, this is a part written by Delbruck, say, according to the conception, this is the penultimate paragraph of the paper, okay? The penultimate paragraph. According to the conception of many biologists, and here they're thinking, Delbruck is thinking of Müller, okay? The genome is a highly complicated chemical physical structure consisting of a series of specific chemical pieces of matter. Okay, so the gene is material, is physical. This was not at the time necessarily the consensus view. The individual genes. Some attempts have been made to project back theoretically, okay, from the organism to its individual genes. The genes are thus conceived as the immediate starting points of the chains of reaction comprising the developmental process. I'm sure that rings a bell now, right, for all of you. That genes are being attributed that importance of initiating the chains of reaction of development, right? The genes, this conception leads to an explicit or implicit critique of the cell theory in the sense that the cell, far from proving itself so magnificently as a unit of life, dissolves into the ultimate units of life, the genes, okay? So Delbruck is saying, well, this is the view that many geneticists have, or some, thinking of specifically of Müller that he mentions in the previous paragraph. And this is the view that Schrödinger puts forward in What is Life? But when you actually look at the paper, the paragraph that follows immediately this one, so this is what you find in the book, the paragraph that follows immediately is one where they are denying and they're rejecting that view. Ideas about the gene challenge this picture. Genes are physical chemical units, okay, they're material, but they're likely incapable of directly forming the morphogenic substances. They also can hardly be thought as the starting points of developmental sequences. Therefore, we need not dissolve the cell into genes, and the starting points of the developmental sequences are not attributed to individual genes, but rather to operations of the cell or even to intercellular processes, right? So you have a completely different view, which is the conclusion that Delbruck puts forward, and yet that is sort of forgotten because this paper was never translated into English. It was only translated into English recently by Phil Sloan in a book that he published, a collection of essays that included a translation of this paper called "Creating a Physical Biology." And what you find when you read it is that Schrödinger completely, deliberately misrepresents the claims. Okay. So that's really, so I think that I hope to have shown you that it wasn't inevitable that Schrödinger would advocate a genocentric view. Schrödinger is looking for reasons to defend a genocentric view because that will enable him to provide reasons to have this mechanistic view in life as a way of reacting to that sort of quantum interjection into biology that Jordan and others are doing. He's trying to say, okay, maybe in physics I have lost the battle of the interpretation, but as far as biology is concerned, it's still deterministic all the way down. And so that's why he's drawing on this sort of literature to make that case. What about the denial of order from disorder processes? I mean, it's really quite bizarre for Schrödinger to be saying that order from disorder plays no role. I've already said this. And it's actually difficult to reconcile with what we know Schrödinger believed about the pervasiveness of statistical laws in science, including in biology. Schrödinger is completely aware of Darwinism and Mendelism, and he knows that those principles are statistical. And yet in the book he's saying that those kinds of principles play no role. What's even more odd is that in 1944, in the very same year that What is Life is published, Schrödinger publishes a short paper in Nature called The Statistical Law in Nature, okay, where he essentially contradicts himself because he's saying that, statistical regularities are everywhere, including in biology, and in fact he mentions specifically Darwin's theory and Mendel's principles as paradigmatic examples, right? So what's going on here? I mean, in the same year, you find these two completely different ways of thinking about order. So this just shows that the view that Schrödinger had, that his conclusion that order from disorder plays no role was not inevitable at all. It was actually playing a role, an argumentative role. He wants to delineate, to circumscribe, and this realm of biology so that statistics plays no role for the purposes of defending this mechanistic worldview that the Copenhagen interpretation of quantum mechanics was undermining or had already undermined. So this is just very odd. I mean, even if you think of the cat, of Schrödinger's cat, I'm wearing this T-shirt of the cat. It's really ironic that Schrödinger is remembered for this cat. I mean, people, if you ask anyone on the street, do you know anything about Schrödinger? Well, of course, Schrödinger's cat is dead and alive. What's really ironic is that Schrödinger presents this thought experiment in a paper in 1935 called The Present State of Quantum Mechanics. And this is a diatribe. It's a very aggressively written paper where Schrödinger is complaining about the Copenhagen interpretation. And in correspondence with Einstein, he says, before he writes this paper, he says, I've got this idea of a thought experiment that's going to demonstrate the nonsensical nature of the Copenhagen interpretation with this cat. Okay, so he then presents the idea of the cat as being if we take the Copenhagen interpretation of mechanics seriously, we would need to think of that cat being simultaneously dead and alive, right? And you only the state of the cat only becomes concrete when you open the box. So the observer is playing an active role on the state of the cat, right? And Schrödinger says that makes no sense. And he thought that would convince people of the problems with the Copenhagen interpretation of quantum mechanics. But what happened? What happened was, ironically, this cat became the poster child of that Copenhagen interpretation. Bohr, instead of being appalled and thinking, wow, this demonstrates the problems, no, he embraced the cat as showing how bizarre the quantum world is. So there's this irony, that Schrödinger, his entire life, fought against that sort of indeterministic and epistemically problematic view of nature, and yet that he's remembered for precisely it's forgotten that idea was intended as a critique, as a reductio ad absurdum argument. So in this context, I think this is the context which we should use to try to understand why Schrödinger got interested in biology. He got interested in biology to find reasons to say, well, okay, maybe in physics we can talk about it, but at least in biology, indeterminacy plays no role because you've got order all the way down in the genetic material itself, and you've got order from order. So he seems to have deliberately read only the biological sources that will provide a substantiation of his view. He's got an agenda. Biology is not the end of the analysis. Biology is just a tool. It's a means to an end. Biology for Schrödinger is just a tool that Schrödinger can use to sort of continue that debate in physics. And so that's the order from disorder. And I also want to mention stochasticity, right? I also made that claim that is implied by Schrödinger's argument of biological order. That seems difficult to excuse because at the time when Schrödinger delivers his lectures, it was well known that stochasticity plays a role. This is not something that we've learned recently. It's something that we've had to remind ourselves recently, but something that we've known for about 100 years. Just think of Darcy Thompson, who wrote in 1917 this fantastic treatise which sought to apply mathematics and physics to biological problems. And Darcy Thompson actually writes, and this is in the second edition, still before what is the lectures of Schrödinger, he says, where he's basically saying that in the microscopic realm where bacteria live, where proteins exist, we have to take seriously Brownian motion. Gravitation is forgotten. The world, the water behaves differently, and the world where they exist is defined, he says, by the molecular shocks of the Brownian movement, and also electrostatic interactions, van der Waals interactions. These are the forces that characterize the world in which molecules exist. Right? Darcy Thompson is saying that molecular biologists seem to have forgotten about that, and now we seem to need to remind ourselves that we need to take Brownian motion seriously if we want to understand gene expression, if we want to understand protein synthesis, if we want to understand metabolism. So here, I think, is where Schrödinger seems to have played a role in my reading of that history. Okay, so let me just briefly conclude. What is life? I think this is incontrovertible, I don't want to dispute this, that the book did intensify the focus on the molecular basis of hereditary. Schrödinger is talking about the genes, and that seems to have prompted some sort of research in that area, but we should remember that the concern of Schrödinger is not genes. Watson is wrong in saying that the book was about genes. The concern of Schrödinger is order, is the nature of biological order. Schrödinger's belief that biological macromolecules must be extremely rigid and stable in order to withstand the disruptive effects of thermal agitation prompted, I suggest, researchers to develop highly idealized models of cellular processes, the ones I showed you that look like circuits, making them less disposed to explore how the cell actually harnesses noise to generate order. This is a very important area of research today, but not 30 years ago, today. And it seems like we have had to unlearn the lessons that Schrödinger gave us to remind ourselves that proteins are molecules, and because they're molecules, they're subject to thermal agitation, and consequently we need to reckon with stochasticity to make sense of cellular order. In a way that we need to remember that that's important. And again, I've already mentioned this. What is life really, in my opinion, should not be understood as an attempt by Schrödinger to advance biology. It should rather be seen as Schrödinger's wistful attempt to salvage this mechanicist and determinist worldview that had been undermined by the advent of quantum mechanics. That's what Schrödinger was really interested in. In that debate with Bohr and Heisenberg and others about how we should think about nature. Is nature indeterministic all the way down? This is just a thought to amuse you. What would have happened if Schrödinger had wanted to defend a different view of nature? A different answer to what is life. Maybe molecular biology might have developed differently. Perhaps, quantum biology now, it's a sort of an emerging field of research. Maybe quantum biology would have emerged much earlier in the 1950s if Schrödinger had suggested that quantum effects, and indeterminacy are important in life, which of course they are in some respects. But, there's been a sort of half a century delay in the development of quantum biology, I would suggest, as a consequence of the influence that Schrödinger's arguments exerted in molecular biology. And finally, and this is the sort of irony, that it may turn out that one of the greatest physicists of the 20th century directly contributed to making several generations of molecular biologists forget about the importance of physical forces on the phenomena they study. I mean, think of the subtitle of the book. The book is called What is Life? The Physical Aspect of the Living Cell. Well, the physical aspect of the living cell is precisely what Schrödinger obscured. And it seems like kind of really ironic, that the great physicist, led to that obscuring of the importance of physics in biology. Thanks for your attention. ¿Preguntas?
Muchas gracias, Manu.
Sí.
Es súper interesante revisitar este libro de Schrödinger y me gusta muchísimo que quites ese anacronismo de que es el antecedente de los biólogos moleculares y que más bien lo pongas en conversación como con los físicos.
Sí.
Pero te quisiera preguntar qué papel juega ahí el Green Paper de Brooks, sobre todo Müller. Hay una serie de ideas que después podemos discutir, pero hay un paper muy importante de Müller de 1922 que es justamente lo contrario. ¿Cómo es que algo tan estable, ¿no? Los conejos siempre producen conejitos, ¿no? Puede cambiar. O sea, él empieza este artículo que se llama algo así como The gene as the origin as the cause of change, debido a no me acuerdo cómo se llama, 1922, y que es la base después de los experimentos con rayos X para provocar mutaciones. Y lo que él dice es por qué la vida es tan ordenada pero a la vez puede cambiar, ¿no? Porque la vida es material y justo usa la metáfora de un cristal, ¿no? Entonces creo que aquí, o sea, voy a hacer como una abogada del diablo de Schrödinger. Creo que Schrödinger es un intermediario y cada quien lo va a utilizar como se le va a dar la gana. O sea, todos estos ejemplos que pusiste de los victoriosos como Watson, Crick, Stein, que lo ponen como antecedentes, sabemos que hay un objetivo ahí profesional de legitimarlo, ¿no? Y poner como este fundador de la mecánica cuántica que se hubiera vuelto a morir cuando se llega, es el fundador de biología molecular, cuando en realidad él está, la estructura del libro es un pésimo argumento de lo que ya se sabía de la biología en ese momento, o sea, de la gente que sabía muchísimo de biología como Müller, porque que quizás era totalmente un genocentrista, pero que quizás era el que más había reflexionado como la materialidad de la vida en ese momento.
Exacto, sí.
Y que justamente es el que ayuda a diseñar el experimento de Delbruck y de Timo Fayet.
No, de hecho, colabora con él, sí, hay una conexión directa.
Entonces, también podemos verlo, sí, en conversación con los físicos,
Sí.
pero como un mal traductor, no como un mal traductor, como un divulgador de la biología, ¿no? Que ni siquiera está realmente teniendo una conversación seria quizás con quien debería de tenerla, que es Müller.
Sí.
¿Cómo verías esa interpretación?
Bueno, muy interesante. A ver, una cosa que no he mencionado que es muy importante es que lo que Schrödinger ofrece no solo es un modelo de estabilidad del gen, sino también un modelo también de variabilidad. Tiene que explicar la mutación, ¿no? Entonces ahí habla de quantum jumps, saltos cuánticos para explicar. Entonces, todo está basado en la mecánica cuántica, pero lo importante es que no solo explicas estabilidad, pero también explicas variabilidad. Eso no lo he mencionado y tenía que haberlo mencionado, es culpa mía. Porque esto, de hecho, Schrödinger lo dice, ¿vale? Pero me he centrado más en el enfoque de estabilidad porque es tan importante para lo que yo considero que es el argumento que está esbozando con respecto al orden biológico. Entonces, ahí la variabilidad, yo creo que ahí forma parte de la idea que tiene Schrödinger, del gen. Con respecto a si él, bueno, que tendría que haber estado en conversación con Müller, pues mira, Müller escribe una reseña del libro, en The Quarterly Review of Biology, del libro de What is Life, y dice, no, este libro está bien, pero bueno, se ve que Schrödinger no sabe de dónde vienen las ideas que menciona porque se está quejando de que no le menciona a él, ¿no? Que bueno, que es una queja justa, porque en el fondo, como acabas de mencionar, este trabajo que hace Delbruck y Timo Fayet de X-ray mutations, que están usando rayos X para causar mutaciones, en realidad está, como dices tú, está propulsado por Müller, ¿no? Que está trabajando con... entonces ahí está claro que Müller es la base y yo creo que eso es evidente cuando miras un poco bueno, pues los antecedentes, ¿no? Pero sí, yo creo que, a ver, Müller, muy curiosamente, publica un artículo donde pide que los físicos se metan para ayudarnos a los genetistas a solucionar estos problemas. Lo dice así, tiene la última frase del paper es ¿quién va a levantarse y ayudarnos, ¿no? ¿Qué físico? Entonces, es curioso, ¿no? que uno podría leer lo que hace Schrödinger como exactamente respondiendo a esa llamada que Müller hace, ¿no? Y yo creo que Müller pues, estaría contento con la visión que Schrödinger ofrece, porque creo que es una visión que tiene la raíz en las ideas que tiene Müller. Pero bueno, lo que yo quiero decir es que esa no es la única idea que existe en el estudio de la genética del momento. O sea, incluso, a ver, la idea de que el gen es responsable de todo es algo que es muy controvertido, es muy polémico, ¿no? Pero parece que si tú no sabes de historia y lees a Schrödinger, pues concluyes que todo el mundo pensaba así, pero no es el caso, ¿no? Incluso la idea de que los genes son materias, es una entidad material, ¿no? Entonces, claro, entonces eso lo puedes trazar a Müller. No sé si había alguna otra cosa que querías que comentase con respecto a esto.
Siento que o sea, me parece muy interesante ponerlo
Sí.
en conversación con los físicos.
Sí.
Pero entonces también en por ejemplo, que quizás con quien está estableciendo un diálogo, incluso aunque él no lo sepa,
Sí.
es con Müller,
Sí.
¿no?
Sí.
O sea, por el lado de...
Sí.
Y que en realidad hay una serie de libros que son interesantes en la historia de la biología del siglo XX, en donde como que los físicos están traduciendo, ¿no? De cierta manera, o los moleculares traduciendo lo que los evolucionistas en un lenguaje que obviamente simplifica algunas del conocimiento biológico de la época.
Sí.
Pero que sí me parece interesante, que creo que en esta historia necesita tener también como un lugar ahí como muy importante Müller, y el experimento de Delbruck, que además justamente se pone a hacer genética porque quiere llevar la interpretación de Copenhague a la genética, a la biología, ¿no?
Sí.
O sea, ¿cómo entra en juego esa...?
Bueno, es que hay tanto que decir, Edna, que no he mencionado, porque fíjate, Delbruck se interesa en la biología escuchando a Bohr hablando de Light and Life, y buscando esta paradoja, ¿no? Que él esperaba que encontraría en la complementariedad, ¿no? Y entonces mucha gente ha dicho, bueno, Delbrück y Schrödinger son parecidos porque ambos están buscando nuevas leyes, pero eso no está totalmente mal, porque Delbrück está defendiendo esta visión de Bohr, que es indeterminista, y Schrödinger está en completo desacuerdo con esta visión, ¿no? Entonces hay muchos problemas, muy frustrante leer muchas veces la literatura historiográfica porque les ves juntos, ¿no? A Delbrück y a Schrödinger. Claro, entonces eso es muy problemático. Iba a decir algo más, pero se me ha olvidado. Luego igual me recuerdo. Sí.
Muchas gracias por la pregunta y la respuesta. Tenemos como media hora.
Perfecto, muy bien.
¿Quién más quisiera preguntar?
Sí.
Agradecería si nos pudiera dar un ejemplo de un fenómeno en el que un ente viviente, digamos una célula, toma o genera orden desde el desorden.
Bien, pues hay una serie de ejemplos de esto que he tratado. Igual no... A ver, voy a volver a las diapositivas rápidamente. Pues son todos los ejemplos. Pues mira, por un lado tienes ejemplos de autoorganización que se pueden considerar como orden del desorden. O sea, tú tienes pues un conjunto de moléculas, hay una ruptura de simetría que da lugar a un sistema que se mantiene en un estado ordenado, alejado del equilibrio, a través del consumo de energía. Entonces ahí tienes orden generado del desorden. Y bueno, los organismos son, en ese sentido, sistemas autoorganizativos, ¿cómo se dice? Pero también hay ejemplos concretos dentro de la célula de organelos que se constituyen de esa misma manera, que esa estabilidad no es una estabilidad fija, no es una estabilidad estática, sino es una estabilidad dinámica. O sea, tú lo observas en un microscopio y no puedes, si es algo que no está, que es como un cross-section, ¿no? Un slice de tiempo, pues no sabes, no lo puedes reconocer, pero si tú observas la célula in vivo, ¿no? Y la observas temporalmente, lo que te das cuenta es que muchas estructuras ordenadas luego se desorganizan, entonces hay mucho más dinamismo y eso creo que son ejemplos claros de organización que proceden de partes o de unos indicios que son estocásticos, ¿no? El otro ejemplo que doy, te puedo hablar un poco del trinquete browniano, para darte un ejemplo más concreto. Pues mira, el círculo representa una molécula, ¿vale? La proteína, una quinesina. Y entonces lo que estás intentando explicar es cómo una quinesina puede puede moverse en una línea recta, ¿vale? No de una manera estocástica, es una línea recta. La interpretación mecánica es que la quinesina está caminando. No sé si has visto los vídeos de la quinesina caminando. Esa interpretación es muy problemática porque no hay una correlación entre el paso. Hay un montón de problemas que trato en el paper que he mencionado si te interesan. A veces las proteínas caminan para atrás y luego para adelante, algunas solo tienen una pierna, entonces parece que están cojeando, ¿no? Entonces no está muy claro. Entonces este modelo, que es un modelo pues muy diferente porque no apela a la estructura de la proteína, lo que sugiere es precisamente esto, ¿no? De que tienes dos procesos que son desordenados, que son por un lado el movimiento estocástico de la proteína cuando en la posición A y C, es que igual lo tengo que explicar mejor. El modelo lo que sugiere es que la proteína tiene dos conformaciones, ¿ok? Una que está representada en el círculo blanco y la otra gris, ¿ok? Y la proteína cambia de conformación cuando utiliza ATP, ¿ok? Cuando consume energía. ¿Y qué ocurre? Cuando consume energía, la conformación de la proteína es tal que tiene un landscape energético que pasa de ser totalmente llano a tener esta estructura, ¿no? Y lo que hace es que la proteína misma tenga una tendencia a moverse a la conformación que es energéticamente más estable. Entonces, lo que sugiere este modelo, y esto es un modelo, es que de esa manera, combinando, como veis aquí, A, B, C y D, pues cuando tienes estocasticidad, el movimiento neto es un movimiento direccional. Entonces, Te puedo dar más detalles, pero bueno, esa es la base del modelo, y ahí lo que creo que tenemos entre manos es una pues, orden del desorden, ¿no? Tienes un orden que se genera a través del movimiento desordenado. Entonces, eso sería otro ejemplo.
Ok, gracias.
Sí.
Yo tengo una pregunta. Bueno, no es una pregunta, es más bien un comentario.
Sí.
Me gustan este tipo de pláticas porque es una crítica a un pensamiento, más bien, algo que parece ser una naturaleza humana. ¿Y a qué voy con esto? Parece ser que los humanos siempre, no solo los científicos, en general, tratamos de partir del orden o buscar el orden. O buscar la regla, tratar de encasillar todo, ponerle nombres a todo, clasificar todo. Los biólogos somos muy buenos para eso. Entonces, más que crucificar a Schrödinger por esa visión, pues creo que es más bien un ejemplo de la naturaleza humana, de cómo siempre tratamos de buscarle un orden a todo, aunque eso no sea lo que realmente está pasando.
Sí.
Eso es lo que, por eso me gustan este tipo de cosas, porque básicamente es como el fenómeno humano. No puedo decir que existen otros animales no humanos porque no me comunico con ellos, pero parece ser una característica humana que realmente es interesante, y más allá de eso puede llegar a ser complicada, porque dentro de esta característica nuestra podemos llegar a hacer asunciones que perduran por mucho tiempo, como la teoría de Darwin, que pueden llegar a tener muchas complicaciones después, o lo mismo que dijo Schrödinger, ¿no? Ese genocentrismo del que hasta la fecha muchos biólogos son afines a.
No, sí, me gustaría pensar que la responsabilidad del científico es una responsabilidad importante que tiene el científico cuando observa, estudia la naturaleza, bueno, pues no dejarse llevar demasiado o cegarse por sus propias preconcepciones o por sus deseos de lo que le gustaría que fuese la naturaleza, ¿no? Entonces, eso claramente muchas veces no se da, pero bueno, un estudio riguroso científico, me imagino que me gustaría pensar que es uno en el cual si el fenómeno que tú estás estudiando no se comporta como tú esperas, pues lo tienes que aceptar, ¿no? Que si no se comporta de manera ordenada, pues no es ordenado. Igual es que las cosas no son ordenadas. Lo que pasa es que la ideología, la ontología, la visión de la naturaleza que suelen tener los científicos, pues suelen influir de una manera tácita, ¿no? Que no es explícita, en cómo pues, los científicos pues, buscan explicaciones, el tipo de interpretaciones que dan. Entonces, Schrödinger, por ejemplo, con esta obsesión que tiene con rescatar, con proteger esta visión del siglo XIX, ¿no? Ordenada del mundo, bueno, pues está por encima de todo. O sea, eso es meta empírico. O sea, eso está primero. Y luego ya todo lo que viene, o sea, toda la ciencia, todo lo que él mira, todo lo que él interpreta, simplemente son herramientas para fortalecer esa preconcepción que, como tú dices, es quizá un deseo que tenemos, ¿no? De orden. Pero creo que eso es algo que tenemos que reconocer como una responsabilidad de la ciencia, ¿no? De no dejarnos llevar demasiado, ¿no? Por lo que nosotros esperamos, porque por supuesto una visión de la naturaleza que es indeterminista, que es toda estocástica, pues igual nos hace sentirnos menos cómodos, ¿no? Pero bueno, pero si es que es así, ¿qué hacemos? ¿Sabes? Entonces ahí está la cuestión, que en la física eso parece que se ha aceptado, ¿no? Esta interpretación de Copenhague es el consenso hoy en día incluso. En la biología, ¿no? En la biología pues tenemos todavía esta obsesión con proteger esta visión ordenada de la célula como una máquina perfecta que hace todo de una manera, ¿sabes? Y que es todo organizado y tal. Entonces, mucho de mi trabajo, de hecho, está intentando pues, desmantelar esta visión que es tan cómoda para nosotros y demostrar que empíricamente tiene muchos problemas.
Para abordar es cómodo hacer eso.
Claro, sí.
Pero no deberíamos perder ese enfoque, por lo menos no como científicos.
Claro, sí, sí.
Esta última parte de la respuesta de Dani tiene que ver con su programa de investigación hacia una interpretación procesual
Sí.
en biología, ¿no? De esto trató el taller y me sirve este comentario que estoy haciendo para comentar también que tenemos las grabaciones del taller, entonces en el intercambio de correos que hagamos en días próximos
Sí.
pongamos de acuerdo acerca de la posibilidad de regresar al taller, ¿no?
Sí, a ver, el taller son 3 sesiones de 2 horas cada uno demostrando los problemas con esta visión mecánica de la vida, ¿no? Tiene muchos problemas. Entonces, eso es lo que trata el taller. Pero la razón por la que la tenemos es en parte porque lo que estás diciendo tú, porque es que nos es muy cómoda, porque nos permite analizar las cosas. Si tenemos esa visión mecánica, pues puedes descomponer el sistema que estás estudiando y puedes analizar sus componentes y no estás perdiendo información y luego los puedes volver a reconstruir. Todo eso son ideas que son muy cómodas, que son muy atractivas y que forman parte del legado, bueno, pues del siglo XVII, en realidad, de la creación de la ciencia moderna, pero son ideas que tienen que someterse a la realidad empírica. Y si los datos nos dicen que esto no, bueno, que estas ideas son problemáticas, tenemos que, creo, pues tomarlos en cuenta, ¿no? Tomarlos en serio.
Ya no tenemos mucho tiempo, me equivoqué hace rato. Está Alfredo en la lista, luego yo tenía un par de preguntas y luego acabo de ver una
Sí.
mano por acá. Entonces, creo que ahí ya...
Bien, yo pregunto brevemente.
Muchas gracias por la plática tan interesante, ilustrativa, un poquito menos subversiva que las otras. En esta discusión sobre qué es lo que el motivo por el que Schrödinger intenta armar un discurso para sostener una idea, da la impresión de que solo hay un motivo pues, natural, humano. ¿Podrías, a lo mejor existe algún motivo social o político que hiciera que esta edición fuera lo que él expresara? Un poco recordando a estas ideas de la física social de muchos, 2, 3 siglos antes, ahora no recuerdo los autores, pero acabo de ver un libro donde toda la introducción es un físico, el libro se llama Masa Crítica, donde él es físico, donde pretende argumentar, inglés, donde pretende argumentar que hay posibilidades que a través de la física se puede explicar los comportamientos sociales. Entonces, es realmente solo intelectual este posicionamiento como cuando Einstein decía a Bohr que el viejo no juega los dados y aquel le decía, ¿y tú quién eres para...?
Pues que Einstein y Schrödinger están en la misma posición. Einstein rechaza esa interpretación hablando de que Dios no juega los dados y Schrödinger con el gato. Pero bueno, al final perdieron esa batalla, porque los físicos de hoy en día... Sí, a ver, pues mira, un ejemplo, no se me ocurren ahora mismo motivaciones políticas por las que Schrödinger quiso defender la visión que defiende, pero hay una razón personal. Él es vienés, se considera heredero de la visión de Boltzmann y toda su visión y todo su trabajo en física, él interpreta su propio trabajo como un intento de reconciliar y de sostener y de defender esa visión de Boltzmann, de la naturaleza donde hay orden. Vale, que igual el orden es solo estadístico, que ya no estamos con Newton y no hay orden a nivel microscópico, porque la termodinámica ha demostrado que a nivel molecular no hay orden. Vale, pero por lo menos hay orden a nivel estadístico. Entonces podemos estar cómodos sabiendo que al fin, en el último término, pues podemos seguir hablando de una ontología ordenada, y eso es lo que la física cuántica pues destruye un poco esa idea. Entonces Schrödinger se le puede leer incluso como el último físico clásico, ¿no?, que está intentando defender esta visión. El resto de sus días que pasa después de esta publicación de What is Life los dedica a intentar reconciliar, ¿no?, lo que está desarrollando una visión de campos de física para poder solventar lo que él veía como inconsistencias en la interpretación cuántica de Bohr, pero que eso al final no tiene éxito, ¿no? Entonces, no sé, los biólogos no lo hablan y los físicos tampoco hablan mucho de What is Life porque los físicos no saben sobre biología. Entonces, en realidad hace falta alguien que pueda combinar un poco esas dos cosas para que lo que yo pienso sea que tengamos una visión, creo, más objetiva, más justa del legado del libro.
Bueno, me toca.
Sí.
Yo tengo 3 preguntas, solo voy a plantear 2. Una sí me gustaría que...
Por supuesto, sí.
Si gustas, nos des un poco la respuesta. Bueno, la primera tendría que ver y es la que creo que me parece más interesante, con lo que hace algunas semanas estábamos platicando respecto a que es este 75 aniversario del libro de Schrödinger y ya también estamos en internacionales, pero tú ya sabías, desde abril nos reunimos en persona en Viena, el profesor Antonio Lascano Araujo, que trabaja en esta facultad, tiene una interpretación acerca del legado de este libro. Esa es la pregunta que me gustaría que, si tienes algún comentario, ya que tú has visto la conferencia que impartió en el Colegio Nacional,
sí.
¿de qué manera difiere, digamos, en los énfasis que él hace allí respecto a tu recuento historiográfico?
Sí.
Luego, otra cuestión tiene que ver con los desarrollos recientes de la filosofía de la biología y ubicándote a ti en una de las tendencias, digamos, más de vanguardia en el mundo, junto con pues, los personajes que mencionamos al principio, ¿no? John Dupré, que estuvo aquí hace unas semanas, y todos los otros personajes muy prominentes en el horizonte de la filosofía de la biología. ¿Por qué crees que se ha tardado este tipo de reflexión crítica acerca de los temas?
¿Por qué se ha
tardado
en hacerse esta... Sí, sí, sí.
Tendrá que ver con lo que también mencionaste durante el taller la semana pasada, la influencia que tuvieron ciertos filósofos de la biología como David Hall, Elliot Sober, Michael Ruse, que podríamos ahora calificarlos de conservadores, y que por el modo que ellos estaban alineándose con las discusiones que los mismos biólogos evolutivos que eran las importantes, si esto es algo que también podríamos, digamos, tomar en cuenta para...
Sí. A ver, en términos de filosóficos, las discusiones de orden, por ejemplo, pues sí, es verdad que no forman parte del itinerario, ¿no?, de la filosofía de la biología cuando se consolida, años 70, años 80, porque bueno, pues los intereses eran otros. Los intereses eran genética de poblaciones y las cuestiones son de evolución por cuestiones históricas que son muy interesantes, pero que no necesariamente vienen al caso, ¿no? En relación de qué tipo de biólogos son los que Hall y Ruse emplean o se inspiran para desarrollar un discurso filosófico, gente como Meyer, Dobzhansky, Simpson. Y bueno, pues entonces todo el lado de la biología molecular pues se deja un poco a un lado. Pero bueno, creo que hoy en día pues no tenemos ya ese sesgo tan evidente, ¿no? Hay mucha gente que trabaja el tema del orden y que trabaja la biología molecular. En el campo de la historia de la biología es un poco diferente, porque en la historia de la biología sí que hay una tradición bastante antigua de estudiar la biología molecular, incluso de cuando la biología molecular todavía estaba, bueno, pues en fermento, ¿no? Bob Olby, Judson están ya escribiendo monografías monografías estudiando el impacto, ¿no?, de estas ideas de biología molecular, y ahí Schrödinger sí que aparece, pero bueno, una cosa que a mí no me gusta de ese tipo de tratamiento de Schrödinger es eso, ¿no?, es el decir, pues mira, como historiador yo no me puedo fiar de lo que dice un científico de la historia, porque el científico tiene su agenda, yo como historiador no. Entonces, si el científico dice que Schrödinger fue muy importante, pues mira, ¿yo qué voy a decir? Pues que está usando a Schrödinger para legitimar, es lo que he dicho antes. Eso es el consenso hoy en día, o sea, y yo creo que por eso quizá este libro no se ha tratado tanto, porque se llegó a esa conclusión a finales de los 80, principios de los 90, Nina Aviram, Evelyn Fox Keller, Lily Kay, que dijeron, mira, este libro fue una herramienta para legitimar y ya. Pero lo que yo estoy intentando hacer en este trabajo, que es que no se está haciendo, es ¿qué dijo Schrödinger? Leer el libro, que son solo 90 páginas. ¿Qué está diciendo? ¿Cuál es el argumento? Es sobre orden. ¿Por qué dice esto? ¿Por qué se mete en la biología? Y si estudias eso, lo que te das cuenta es que hay lo que yo creo que una serie de razones y de motivaciones que Schrödinger tiene de por qué defiende esta visión reduccionista y mecanicista y determinista. ¿Por qué se apoya en Müller y no se apoya en otros genetistas? ¿Por qué deliberadamente interpreta mal las conclusiones del paper de Delbruck, ¿no? Yo creo que ahí eso es importante. Con respecto a lo de Lazcano, bueno, pues sí, él he visto esta plática que ha ofrecido, y bueno, pues yo creo que se cierne a la interpretación más convencional, ¿no?, del papel de Schrödinger, porque creo que es la interpretación que uno llega si no analiza el contexto histórico. Es que hay que hacer un trabajo histórico, o sea, hay que mirar la correspondencia, hay que mirar con quién está hablando Schrödinger, qué biólogos está leyendo y por qué lee eso sino otros, ¿no? Porque en el fondo el libro tampoco menciona a muchos biólogos, ¿entiendes? No menciona a Müller, por eso Müller se enfada. Menciona a Delbruck, ¿no? Entonces la gente piensa, no, claro, Delbruck pues tenía la misma idea que Schrödinger, eso no es correcto, ¿no? Entonces hay que hacer un trabajo histórico serio, de mirar los archivos, mirar las correspondencias para entender por qué Schrödinger dijo lo que dijo.
Bueno, la tercera solo la
Sí.
es acerca de las vinculaciones que yo vi entre lo que dijiste hoy y lo que dijiste ayer.
Sí.
Es decir, hay un ocultamiento o una marginación del
Sí.
discurso organicista,
Sí.
¿verdad? De las décadas de los 30.
Sí, sí, sí.
Cuando hablaste de la conexión con Friedland,
Sí.
los dos hermanos,
Sí.
claramente allí, yo leí entre líneas que
Sí.
estabas un poco haciendo un guiño a algunas de las cosas.
Sí, es muy interesante, hay tanto que decir y no hay tiempo, pero mira, Jordan, que está intentando ofrecer esta visión biológica indeterminista, está en correspondencia con Bertalanffy, con organicistas, ¿no? Hay como los mismos organicistas, estos biólogos de entreguerras, quieren apoyarse en la mecánica cuántica de alguna manera para ofrecer una base nueva teórica para la biología. O sea, ellos consideran que esta revolución en la física a principios del siglo XX va a dar lugar a una revolución en la biología y que ellos van a ser responsables en producir, que luego no se da, ¿no? La revolución es una revolución del siglo XIX casi, ¿no? Determinista clásica de que es la revolución de la biología molecular, incluyendo, por supuesto, cibernética e información, pero bueno, en realidad la visión es más clásica, ¿no? Entonces, por supuesto, si tú te das cuenta o empiezas a mirarlo, lo que ves es que estas personas que Schrödinger está criticando, bueno, toda esta escuela de Bohr, son los físicos que los biólogos de la época, muchos biólogos de la época, los organicistas en particular, están queriendo conectarse, están queriendo asemejarse porque ellos creen que la biología... Porque en el fondo, esta visión indeterminista como que se acerca más a lo que los biólogos durante muchísimos siglos llevan estudiando, ¿no? El orden, los campos, esta estocasticidad. Entonces, de alguna manera, lo que los organicistas creen es que apelando a esta nueva física podemos tener una mejor base teórica para la biología, pero en el fondo Schrödinger gana esa batalla en ese sentido porque, ¿sabes?, la noción de orden y de organización no es una noción estocástica y dinámica, es una noción muy rígida, ¿no? Entonces ese debate tan rico en los años 30 entre físicos y biólogos, ¿no?, sobre la ontología de la vida se empobrece, se pierde, ¿no? Y eso también se tiene que redescubrir históricamente.
Pues, la última pregunta.
Sí, mira, algo. Bueno, como alguien no le he entrado, me considero en ese tipo de temas que me son nuevos, pero no voy a comentar a la compañera que a veces está este impulso de querer darle una conciencia o un aspecto humano a las cosas, ¿no? Y yo lo digo, es un comentario, y quería preguntarte cómo lo ves. A veces, como público al que va enfocada la divulgación de la ciencia y todo ese tipo de cosas, incluso como estudiante de biología, pues cuesta trabajo integrar este tipo de pláticas, pues, este tipo de temas. Y yo digo, bueno, si ya le dedicas cierto tiempo a estudiar y más o menos empiezas a adentrarte dentro de ese tópico, para alguien de afuera totalmente es ajeno.
¿Pero qué es lo que cuesta trabajo integrar exactamente?
Por ejemplo, los conceptos como lo que manejabas de feminismo.
Sí.
De hecho, te iba a preguntar ¿por qué hacía la referencia o la comparación del cristal, por ejemplo?
¿Por qué se hace la referencia? Porque el cristal ofrece una entidad estable y fija que puede mantener un orden a pesar de la agitación termal del movimiento browniano. Entonces, la caracterización del ADN como un cristal está motivada con la intención de eliminar todo lo que es el ambiente físico. O sea, en el fondo, esta idea la motivación es olvidarte del ambiente, ¿no? Es decir, bueno, pues si quieres entender el orden, te centras solo en la estructura interna de la molécula. Y claro, esa es una idea muy potente y muy influyente en la segunda mitad del siglo XX, porque en el fondo la biología molecular es lo que hace. La biología molecular no estudia sistemas, no estudia ni siquiera interacciones muchas veces. Lo que estudia es la estructura y la especificidad funcional de una molécula, de una proteína, por ejemplo. Entonces, yo lo que estoy diciendo es que igual esa idea perfectamente está como anticipada por la idea de Schrödinger, sí.
Entonces sería un reflejo de lo que estaba en boga en ese tiempo.
Pues no, exactamente no. O sea, yo lo que he intentado también explicar en la charla es que hay un empobrecimiento del discurso en el momento cuando Schrödinger está escribiendo o está dando las charlas, los lectures de What is Life, acerca de cómo debemos de concebir las moléculas, ¿no? Lo que estoy diciendo es que precisamente en esa época no sería raro encontrarte a gente que dice, no, si quieres entender el desarrollo, olvídate no tomes el ADN o el cromosoma como la base. Tenemos que tener una visión mucho más sistémica. Pero luego como se pierde, ¿no? Y lo estamos redescubriendo ahora. O sea, medio siglo después estamos volviendo a donde estábamos justo antes de que Schrödinger de alguna manera triunfase con su interpretación reduccionista. Entonces, por eso es interesante ver esta historia. Aunque no te interese nada la historia, es interesante, yo creo, para un científico, el entender por qué nos encantan, yo qué sé, este discurso de máquinas o por qué tenemos estas representaciones de ingeniería, ¿no? De circuitos. Quizá, yo esto solo lo propongo como posible explicación de por qué nos gusta tanto, que tiene que ver con el legado, ¿no? Intelectual de las personas que como Schrödinger, que trataron este tema de una manera muy influyente. Sí, exacto. Sí, por eso ese trabajo histórico es tan importante, ¿no? Porque nos abre, nos damos cuenta que la visión que tenemos no es inevitable. No es inevitable tener una visión genocentrista. La historia lo que te da es pues un panorama te ve mucho más amplio, ¿no? De distintas maneras de conceptualizar algo. Hoy en día incluso, ¿eh? Entonces creo que por eso creo que este tipo de trabajo debería, en principio al menos, ser de interés no solo para un historiador que le interesa lo que sabe, lo que dijo Schrödinger.
Todas las analogías a máquinas,
sí.
a
Sí.
¿Es lo que se le consideraría un efecto del positivismo en la ciencia?
No únicamente. O sea, la analogía con la máquina la puedes encontrar, bueno, de muchísimos pensadores desde Descartes, siglo XVII hasta hoy en día. Tiene mi taller de la semana pasada fue todo sobre eso. Igual interesa verlas. Si te interesa la razón por la que los biólogos les gusta o se han sentido atraídos por conceptualizar la vida de una manera mecánica, eso es lo que he tratado en mecanicismo.
Bueno, pues desde mi punto de vista fue un par de semanas excelentes, muy estimulantes intelectualmente. Te agradecemos mucho, Dani, que hayas aceptado la invitación a México y ojalá pues no sea la última vez que vengas.
Muchas gracias.
Ya hemos empezado a platicar. Posibilidad de que vengas el próximo año, pronto. Entonces, pues yo les pediría que le demos un aplauso a Dani, que pues... Pues sin más.
Ya está. Bien.